Uh, Assalamu alaikum, everyone. Dear students, I hope you are fine and doing well. It's a pleasure to welcome you all once again. Today, I am come up with another series of my lecture on data encryption standard. So, that's basically I just start up with one of the student in online session. There are basically two way to cope up with this online series and learning or in virtual distance learning. And that way I must say that this kind of things are not done by one person. There are these kind of things can be done by a team of people. So let us start with another interactive session of my course, Introduction to Cryptography. So my question, what I would like to present you today is it's all about simplified DES. Means to say, lastly, we have discussed one version of DS on 12 bits, and now we are discussing another modification and a simplified form of DS, data encryption standard, with 8 bits. And moreover, we will basically utilize 4 by 4 substitution box. And another way we can say we have utilized confusion component that map 4 bits on 2 bits. And generally, we call it we have utilized rectangular boxes and compression type substitution boxes. So the idea is basically developed by one of the professor. This name was Professor Edward from Santa Clara University. Dear student, I'm not going to discuss more to what I should say, and let me elaborate some topic which will be quite useful for today discussion. So in today we will cover basically, of course, we will cover something like DES and its small variant, and we call it simplified DES. Let us come up with the idea. So simplified DES consists of a 8-bit plain text and substitution boxes of 4 by 4. That there are basically two types, two substitution boxes that map 4 bits on 2 bits. And you must keep one thing in your mind, that each row is non-repeating, and each there are 4 rows in each of the substitution box in simplified DS, and each row is fundamentally a one substitution box. So if I can say uh, there are 2 substitution box, and inside 2 substitution box, the each and every row is there should not be a repeated elements, and both in each and every row of our substitution boxes in simplified uh, DES consists of the element of GF 2 raised to power 2, means to say Galva field with 2 elements. So let me go to third slide. Some overview how encryption and decryption will be performed in simplified DES. In encryption, we take basically 8 bits block and then 10 bits key, and input basically produced as an input, and 8-bit key is generated as a input and produce 8-bit block of ciphertext as an output. So in case of decryption, which is a reverse procedure of encryption, in decryption it take an 8-bit block of ciphertext and the same 10 bits key used to produce that ciphertext as input and produce the original 8-bit block of plain text. In that case, let me our topic by the end of this today lecture, believe me, you will be familiar with simplified DES. Don't you worry about handout or slides. Basically, students, I will upload the slides of my lecture on our WhatsApp group, as well as I can email the PowerPoint presentation to anybody who want it. So don't you worry about all this stuff. So let me go into four slides. Fourth slide of my presentation, my today lecture, and is basically the SDS substitution box. Fundamentally, basically SDS simplified data encryption standard consists of five functions, and that consists of basically five functions. First is initial permutation, then if complex function which is consists of substitution as well as permutation component and some uh, uh, binary operation that depend upon key as an input, and a simple permutation function that switch the two half of the data as the swapping function. Then a function we apply once again fk, which is utilized in step 2, and then after performing these four steps, and then finally we will apply initial permutation, and after fifth step we will get our ciphertext. Dear students, let me combine these as sorry, in all these five steps into some standard notation like mathematical equation expression for these five functions. And five function basically SDS. Whenever I say SDS, it's sure I'm talking about simplified data encryption algorithm. So, dear student, as the simplified DES is fundamentally consists of a combination of five functions. So I can write cipher as a composition of five functions. That is initial permutation, FK complex function that is dependent on first key, first sub key, then swapping function. Then and again I apply complex function f, which is based upon based on second key, second sub key, and then finally I have applied inverse permutation. Let me elaborate this in slide number 5. Uh, look at this slide. So dear student, if you can look over this expression, that is, as I told you, this cipher can be gained through composition of a five function. This is initial permutation, that is one of the complex function f of ki that we will discuss in later. So this is swapping function that basically swap left half to right and right half to left. So this is again fk, that it depend upon some composition as well as uh, substitution as well as confusion. Then finally we will have to apply inverse permutation. So one can write it like as we have discussed, composition of f of g is basically f of g of x. So I can write it down like in composition of a function, and our input is here is a plain text, and we will get ciphertext where k1 is P8. Let me tell you, students, the P8 means to say a permutation that apply on basically that will apply on some 8-bit key, and that or 10-bit key, and transmit this from 10 bits we will gain 8 bits. So students, this is all about K2, how one can get K2. We will apply a 2-time shift on our key. First we will apply P10. This is P10 apply on key of having 10 bits, and this perform first left shift. Then after this input output, then we will apply an again shift. It means we apply two shift. Then again we will apply P10, which is a permutation that transform 10 bit into 8 bits. So finally, in the reverse procedure, apply a reverse procedure on ciphertext, we will get back our plain text, which is written again in the form of composition of a functions. Mm, the generic structures of simplified DES is given in figure 1 that can be explained with the help of slide number 5, that I take plain text and apply an key of 10 bits and then apply shift on P10 with the one left shift, then apply, I get K1, and then apply P10 on that, that after shifting the permutation on 10-bit key and then shifting this output and then again apply P10, we will get K1, and this K1 is combined with FK and then swap this input, and then again we will apply this same step and apply two shift on this output that is basically getting from this one, and then again we will apply P8, and then for second, basically second time using FK, we need K to sub key or second sub key, and then apply in inverse permutation. In that case, we will get finally we will get 8-bit ciphertext. So one thing you must keep in your mind that from where you start and then you have to end up with the same number of bits. I means to say I just start with 8-bit plain text, and after shuffling, expansion, like permutation, substitution, that at some time inside the algorithm, some bits can be expanded, then some bits then apply certain operation that expand the bits, and then apply some other operation that basically compress the output inside the basically blocks structure. So ultimately you have to get the same number of bits. So this is a more or less simplified DES block diagram, or one of the generalized diagram for simplified DES. So the reverse procedure is the basically the inverse of encryption algorithm, and this is same as encryption, but in a reverse order. You have to apply on ciphertext and get back your plain text of 8 bits. So let me do it. These are basically standard steps that how to get your how to generate your key in SDS. It depends upon the use of 10-bit key shared between sender and receiver. Since we are working on basically our blocks, basically our let me wait for a while. Let me read something. So basically, the key generation it depend upon 10-bit key, and from this key, two 8-bit sub key are produced for use in particular stages of the encryption as well as decryption algorithm. Firstly, we will have to permute our standard key by using P10. That P10 is basically permutation that basically permute your 10-bit key into 10-bit key in this order. That is third bit of this key of having 10 bits length, which is third bit is placed on first, and a fifth bit of this 10-bit key length is placed on second position, then the second is placed on third, and the seventh is placed on fourth. In that way, 10th K6 is placed on 10th position. So this is one of the type of permutation, that is P10 is nothing. If I can define in term of function, that P10 is a function from Z to 10 to Z to 10. That's it, map 10 tuples on 10 tuples. So next, as we apply P10, next step in key generation is to apply some circular shift. It may be left or it may be right, but in that case, I am using just left circular shift. For getting first sub key, we have to apply one time left shift, and that for getting second sub key, we will have to apply uh, two time left shift. So look at this operation, that is we have basically take first five bits of last steps, that is k1, k2, k3, k4, k5, and then apply left shift of first left shift. It means to say I have just transmitted this k2 last one, and change the position. The second will be placed to first, third will be placed to second, and then fourth will be placed to third, and fifth will be placed to fourth, and the first one is placed from first to fifth position, like this way. Next, apply P10 on this uh, basically the this left shift, one left shift. If you want to apply two left shift, then in that case you have to apply another left shift, then k2 will be transmitted from this first position to fifth position, and then you can subsequently change the position of other keys by one towards left, one position towards left. In that way, k3 will be on first position, K4 will be on second, K5 will be on third, and K1 will be on fourth, and K2 will be on fifth position. And let us go into another step of basic structure of DES, where we have apply P10. How one can apply P10? And P10 is again a permutation that map 10 bits on 8 bits. So let me take this one key of having length 10 bits, then we get 8 bits. Let us say from this we have to permute like compression permutation. P10 is like compression permutation that take larger input and map on smaller output. So this take 10 bits key and map on 7, and like this. First position will take sixth position bit, or sixth position will be placed on first, and third basically k3 is placed on second position, k7 is placed on third position, and then k4 is placed on fourth position, and then k8 is placed on fifth position. And students, you can see other all by yourself, and that's ultimately that will give you the first key after applying k8. The first key sub key is of order of length 8 bits. Similarly, if you can apply to this one. So if you can apply a two times circular shift, and the to get second sub key k2, perform again 2-bit circular shift, then apply this one, and then finally apply p8 again, so you will get the k2. Let us explain key generation with the help of one example. um, Dear student, with the help of this example, you can see over here, we take um, uh, 10 bits as um, how one can permute, apply P10. So you have, say, input of 10 bits, and you take apply P10 on this 10 bit input, and you will get this one. The output will be like this one, and you can see over here, if you can remember P10, what P10 did. Basically on slide number 7, if you can see, over here the P10 did K1, K1, K2, K3, K4, K5, K6, K7, K8, K9, K10. So when we apply this P10 on this 10th length input, then it means K1, K3 is mapped on first position. Here K is like this one. If you can see this over here on uh, seventh slide. K1, K2, K3 on first position, there will be a K3 means to say if the bits on third position will be mapped on first position, and bit on fifth position is mapped on second position, and bit on second position is mapped on third. Like in this way, you can see over here that first bit on third position, that is 1, is a map on first position, and bit on fifth position, that is 0, that is map on second, and second is map on third. And similarly we will perform all these calculation as given in slide number 17. By using this P10, we will apply P10 on this kind of input and get this output. So how one can apply a circular shift? So we divide the output of P10 separately into 5 bits each, and apply this left hand side 5 bits circular shift. Like if you can apply a left circular shift on 100, which is the half of this one 5 bits, then we will get ultimately this one transmitted to last one, and we'll change the position of rest of the bits and towards left. So we'll get to 1 and then apply left shift on right bits, and we will get this one. So pick out the permutation P8 of 10 bits, that is basically if we join these 5 bits and these 5 bits and apply P10, that P10 basically did take 10 bits and map on 8 bits. P10 is a basically a function that take 10 bits and map on 8 bits. So if I can say in term of function, what does it mean? So P10 is a function from z to 10 to z to 8. So it's a map 10 tuples on 8 tuples. And if as a vector space we can talk about, so it's a basically P8 convert 10 dimensional vector space, our binary field, into a 8 dimensional vector space, our binary field Z2. So ultimately we will get K1. This is as this element that we will get after applying P10 on this 10 bit input. This is as a first sub key, and we'll call it K1. Now perform two circular shift on this basically this result, and after applying 2 time circular shift on this, we will get this one, and this P2 on these part 2 time left shift, we will get this one. After applying the if we join these output, this one 0 0 1 0 0, then uh, 0 0 0 1 1. So if we can apply P10 on this, we will get this result of 8 bits. And this is nothing, it is just a second sub key K2. Dear student, we have explained with the help of the key generation of my basically SDS, and this we have explained this with the help of one example in our previous slides. And one thing that has to be in your mind, that we are discussing simplified DES just to realize the situation how basically different variant of data encryption standard is right now in a fashion due to IoT's small lightweight component, or we can say in constraint, not constraint free, it's a constrained devices where we need small memory and small storage spaces. So for that, we have to basically devise some mechanism, and we call the sort of mechanism as a lightweight encryption mechanism. So let me explain this with the help of one example. Um, Let me tell you from slide number 12. Initial and final permutation in SDS is given over here. So you can see initial permutation, what it did, that map 10 bit on 10 bit, first bit, second bit will be on second position. Sorry, second bit will be placed on first position, and sixth bit on second, and third is remain on third, and then first bit on fourth position, and then fourth is placed on fifth position, and then eight is placed on sixth position, and then seven is placed on five is placed on seventh position, and finally seven is placed on eighth position, and the IP inverse, and it's an inverse permutation we will have to apply when we have performed all substitution permutation and all component inside, and then finally we will have to apply an inverse permutation in order to get our 8-bit plain text. So let me start with how one can say how one can generate FK. It's a complex function that consists of substitution as well as diffusion. So let L and R be the left and right half of 8-bit input to FK. Let F be a map from 4-bit string to 4-bit string, and SK be the sub key K1 and K2, and XOR is the binary bit by bit XOR of functions. Or let FK is apply on left and right half, then left half is XOR is FR comma SK comma R. So in that case, we will get basically order pair that will get left and right, and we will generate another order pair in say this one L. This is a completely different from this one. I will and comma R. So dear student, if you can see over here how your expansion function or F mapping or E mapping is working. It take 4-bit as an input and map on 8-bit. So if I can realize the expansion functions, that if you make largest, if you can make laser like focus, then you can see over here EP take basically expansion permutation, take 4-bit and map on 8-bit output. So let me do it. That is when you have 4 input, 1, 2, 3, 4. That is 4. First position is 4, and then second position is 1. Then third position is 2, and fourth position is 3. Then 4, 1, 2, 3. This is one of the expression. If you cannot write like this, then you can write it like this one. So the next block is you have basically 4 bits, so you have to place all 4 bits into 8 bits. So in fifth position you have to place 2, and sixth position you have to place 3, and on seventh position you have to place 4, and then on last position, eighth position, you will have to once again place 1. So basically you have 4 bits, so you have to play with 4 binary bits, and in a different position of 8 position. So 8-bit subkey K is added to output of EB using XOR operation like this one after XORing. So first 4-bit feed to S box, and then S naught uh, first substitution box, we'll call it S0, and this one, and second 4-bit feed to second substitution box, and we'll call it S1. So substitution box uses first and fourth bit to specify the row, and second and third bit to specify the column. Enter the position on base 2 in 2-bit output. the 4-bit produced by S box like S0 and S1 are permuted using P4. So, dear student, I get 2 bits from this while applying 4-bit feed 4-bit in this size box. I will get 2 bits and 2 bits from this substitution box as an output and 2 bits from this substitution as a output. And we can concatenate both these output. We will get 4 bits as an output, and then we will pass 4 bits from this P4 permutation for and P4, I mean to say that map 4-bit into 4-bit in this order like this one. Output of the P4 is output of F. So F is nothing, it is just output of this whole encryption mechanism, and this is output. And you can see over here, these are our substitution boxes, and these are standard substitution boxes that are now used in simplified DES data encryption standard. This is in terms of binary representation, and this is decimal representation of our substitution boxes. So brute force, some analysis of SDS. Brute force attack is feasible, and it's 2 power 10, which is 1025 possible bits. So non-plain text and ciphertext attacks is quite difficult in that case, because we are using some linear as well as non-linear map, which result in a complex uh, basically complex polynomial expression for the ciphertext width, and making crypt analysis linear. Either it may be linear or differential will be quite difficult for passive as well as active attackers. So let us start with one example, that is expansion function, that basically 1, 2, 3, that on expansion function basically give you the idea that how you can map 4-bit on 8 bits. So expansion, here we have 4 element that is map on 8 elements, like fourth position take as a first, and first bit is the position on second, and then second is placed on third, and third is placed on fourth, then the second is placed on, and after 4 we will these elements will be repeated in this order, and we will basically performing permutations. So on fifth position will once again 2, and sixth position will once again 3, and on seventh position we have fourth once again, and on last position, eighth position, we will have once again 1. So from 4 input we have generate 8 output. So initial permutation, that is basically the functions Z210 to Z210, that is map 10 bits on 10 bits in this in this order. That is for 1, 2, 3, 4, and that is 2 is map on first position, and 6 is map on second, and 3 is map on 3. Then 1 is map on fourth position, then 4 is map on fifth position, then uh, 8 is map on sixth position, then fifth is map on seventh position, then 7 is map on eighth position. So, dear student, it's quite interesting examples I have done with where is to take some 8-bit input, and inshallah will generate in next slides number 19. So let me introduce substitution boxes. So the P4 that is apply in that manner. This is placed on this like if you can see my cursor, like second position on first, and fourth position on second, and third is map on third, and first is map on fourth position. So P4 is nothing if I can take in term of a function that take 4 bits and map on 4 bits. That is P4 is a function from Z to 4 to Z to 4. So why I'm calling all the time Z Z24 to Z24. So it's not just I just elaborate and place K1, K2, K3, K4. These are not just some basically other numbers. These are just binary of length 10 having 10 bit key of length 10 bit, and it may be 4 bit, it may be 7 bit, but in that case we are applying. So you p10 basically take 4 bit as an input and map on 4 bit length as an output. So here you can see from this step we will get K1. That K1 is from where we get K1. So this I have take this K1 from my slide where I have applied left and right shift like this one K I have take from that. If you can see over here, uh, let me tell you one thing. Wait. So this one is my K1, 1 0 1 0 1 1 0. So this is I have take it as a K1. So that will be used in next few minutes. So these are basically substitution boxes after the getting K1. Then after getting K1, we will apply substitution boxes, and these are the substitution boxes in terms of binary representation, and this is a decimal representation. Here you can see in my previous discussion, I talk about the each and every row is there will be no repetition, and each and every row is basically the element from Galva field to raised power 2. Galva field having basically four elements, and here you can see 0 1 means to say 1, 0 0 is 0, 1 1 is 3, and 1 0 is 2. So these are basically the binary representation of my first substitution box, and this is binary representation of my second substitution. Similarly, the decimal representation of these substitution box S0 and S1 are given in this way. So how to perform all these steps? Let us take one plain text uh, having length 8 bits. So this one like. So dear student, the first step in simplified DES is how to basically perform all these steps of simplified DES. I will just go through the encryption. The decryption will be left as an exercise. But let us take one plain text of 8 bits, that is 0, uh, double one, 1 0 0 1 0. So I have to apply initial permutation that map 10 bits on 10 bits. So 0 1 1 1. I place my binaries like in this first half chunks and this second half chunks, and this 1 2 3 4 I make them as a first position, second, third, fourth, fifth, sixth, seventh, and eighth position. So if you can see on slide number 17, the initial permutation, the second position is mapped on first position, and here you can see this one. If I can see this one like this, second position is mapped on first one, and sixth position is mapped on second position, and third is remain on third, and then first is map on fourth position. Here you can see over here the first is map on second, and then the second first is map on second means to say this is the second position, this is map on first, and second is map on six means to say this is a sixth position, this is map on second, and third is remain on third. So this is a third bit of our plain text. This is placed on at third position. So fourth position is map on one. That is Fourth is fourth basically the on fourth position is map upon first one, that is first bit of the plain text is 0, so it will be map over here. The on fifth position there will be a fourth bit, so this is the fourth bit. On sixth position there will be 8 bit 8 bit this is 8 bit, this one is eighth bit of our plain text, and the on seventh position will have a fifth bit of our plain text. This is our fifth bit of our plain text. And here you can see on eighth position we have 7 bit of our plain text. So 7 bit of our plain text is 1. In that case, our this input is after applying initial permutation will be the output after applying initial permutation on this input. We will get this output, that is 101010001. So after applying initial permutation on plain text, we will get this as an output. So no, we have to divide the basically the in output of previous step into two equal block of 4 bits, that each is converted into 4 bit, and we will play with right chunks of 4 bits like this one. I place it on with red color and then green color, and I just take the green color 1001 and then apply expansion function. And you know what expansion function did, that is placed on slide number 17. Basically that take 4 bit and map on 8 bit binary vector. So if you can see over here, so when I apply expansion function on right 4 bit chunks, that is 1001, that is 11010011. So that is first position is fourth. You have to place fourth bit on first, then first is on second, that is this one, and then second is on third position, second bit is placed on third position, and the third bit is placed on fourth position, then third bit is placed on fourth position. In that way, in a similar fashion, we will do the rest of the calculation, and we will get 8 bits from 4 bit to 8 bit. If I can define the expansion function in terms of expression, that is this will be a function that take 4 input, whose ground field is Z2, and that map on 8 dimensional vector space our binary field Z2. So this is our first sub key, that is 10100100. So I XOR this expansion with my K1. That's expansion functions. Expansion function. This will be expansion function, and this is our key which we have derived in our last slide number 18, and the key generation of DES slide. So I just make XOR of EP with K1. I get another 8-bit output. So after getting this 8-bit output, then I once again divide this 8 bits into two chunks of 4-4 bit, and just feed it this 4 input to S0, and these remaining 4 bit into S1. The first and fourth position, that is will tell you 00. This is a row, and first, second, and third position will give you the index of column, and then convert this binary to decimal 000, and then again double one in binary to decimal, which is 3. So you take zeroth row and third column, and here you can see, if I can show you the substitution boxes, 0th row and third column, and means to say 0th row, this one, and third column, which is the output is 1 0. So here you can see over here the output will be 1 0. So in similar fashion, you have to perform the calculation for S1, and ultimately I get 10 from S0, and then S1 give me the double one, and I just combine these two bits from S0 and two bits output from S1. You can see over here, basically S0 is nothing, it is just a function from Z to 4 to Z24, and S1 is a function from Z24 to Z24. Basically, this is a type of compression substitution boxes. So this after applying this S0 and S1, dear student, I finally get 4 bits, 1011, and then I call it the S0 and S1, the 1011. Then I apply P4 on this 4 bit basically output of S0 and S1. So after applying 4-bit permutations, it means I just place the position on this 1, 2, 3, 4. This is what you call 1, this one, and 0, second position of the output of after substitution boxes. This is 1, and this is again 1. So this one, so the what P4 did, this P4 for second element is placed on first position, and the fourth element is placed on second position, and third is remain on third, and then first is replaced with the fourth position. So in that case, if second element, this is 0, this is placed over here. The fourth element is 1, this is placed over second position. Then third is 1, this is remain on third position. And then first position, the binary of first position is 1, so we will have to place our at fourth position. Now we take left block of initial permutation to operate rest of the simplified algorithm. So dear students, I take left of the initial permutation, that is 4 bits, 1010, then XOR with the output of P4, that is again 4 bits, 1101. So combining the above output with right hand of the output from initial permutation, that is 1001. So this is our the calculation, and we will combine this with the right hand side of the initial output of initial permutation, and this is the right hand side of initial permutation, and ultimately we, the student, we get 4-bit output. So finally, what we will have to do, we call it as a L0, and this as a L1, and then we will have to use swapping function that swap left chunks to right and right to left. So dear student, here you can see the I just put some colors in order to you can understand how this swapping is performed. This is I highlighted this with L0 with different color, and the R0 with blue color, and this is uh, type of colors, different color with different organization. Sorry, L0 with different color and R0 with different, and then swap these both colors, and ultimately the left is right is on left, and left chunks is placed on right. So we will get ultimately R0 and L0. So the output will be 1001 1101. This will be our first output of first round. So I must say that this is just a simplified encryption algorithm. So dear student, for decryption, you will have to perform the reverse procedure. Okay, I think that's everything I would like to say today about simplified data encryption standard. Finally, I would like to highlight one key point that this type of algorithm nowadays is good for lightweight or constrained environment devices such as Android and other small devices. their security is quite important, play a quite important role in the world of Internet of Things and AI-based devices. So you have to be very much smart by devising some lightweight encryption algorithm. It must have some good cryptographic characteristics while devising any encryption algorithm. These are not just swapping, substitution, permutation. Each and every component while constructing any good encryption algorithm, you have to check the encryption quality of each and every element of your block cipher. And first you have to test whether these substitution boxes which you are going to use in your while constructing your any block cipher, either it is sustainable. I mean to say it must have some good cryptographic characteristics, like it must have a good non-linearity. It has good strict avalanche criteria and bit independent, as well as two other cryptographic attacks that must be that must your substitution box must qualify. These are uh, linear approximation as well as differential approximation probabilities, and that your substitution box must satisfy some characteristics. Then after these characteristics, you have to utilize these linear as well as non-linear component in your block ciphers. So I think I have done a lot. In that current scenario, so we must all behave like a team, and keep one thing in your mind once again, as I discussed in my first slide, that great things are not done by one person. They are they are done by a team of people. So stay tuned to your lecture and stay at home in this current scenario. So thank you all, and please stay at home. Social distance is also quite important. So that's I just place this message for you people. So Allah Hafiz, and there are some good readings material that you have to follow by. These are some references now. So one assignment, you should not be worried about assignments and things. It will be quite easy for you. So you have to take some like 3 by 2 substitution box to perform all these calculation. Either these can it be possible to use 3 by 2 substitution box to perform all simplified DES encryption mechanism, or the other question is use straight substitution box that map 3 bits onto 3 bits and adjust all other steps accordingly. So I end up by don't be scared from assignments. By doing this assignment, you will make mistakes. And believe me, student, a person who never made mistakes never tried any new thing in his life. So Allah Hafiz, and may Allah bless you all, and thank you all.